Hey guys, your boy Chill here. Welcome back to Hardware 3D. In the last video, we did some cube mapping stuff for Skybox. Now we're going to take this cube mapping technology and we're going to apply it to our shadows. So instead of just capturing the shadow map in one direction, we're going to capture shadow map in all directions around a point light and then use that to render and cast shadows in all directions. So, first thing we need some kind of cube texture, depth stencil stuff that is going to be able to work with our shadow mapping. So first come in here, I'm just creating the basic utility types, the bindables that we're going to be using. So if we look at cube texture, I add a new one, I call it depth cube texture. So we got cube texture, we got depth cube texture. And one thing you're going to notice right out of the bat is that depth cube texture has a vector of bindables, of output depth stencils. So this is a bindable that has other bindables inside of it, a composite bindable. And you'll be able to get those depth buffers out by index, by reference here. But what are we actually doing here? Well, let's look at cube-texture.cpp. So if you look at this here, you see it's the same basically as creating a cube texture up here. I'm going to create a texture. It's going to have an array. So we're going to have an array of 2D textures. The format is going to be R32 because this is going to be depth. And what else do we got here? We're going to be able to bind it as a shader resource and also bind it as a depth stencil. We write depth and we read it as a texture cube. So we got to make sure that the flags tell that we're a texture cube. And we create this bad boy. Then we create a view on this bad boy as a texture cube. And this is basically the same as, creating any other shader resource view. Then down here is where things get interesting, because now we got to create the view on the texture as a depth stencil. And the depth stencil view, we're not creating it directly. We are creating output only depth stencil bindables. So these bindables are going to link into this texture. So to do that, when we construct the depth stencil, we're going to pass it a com pointer to the texture resource, and we're going to pass it the index which face this depth stencil is going to be, because this is a texture cube. It's got 6 faces. So each one of these bindables is going to be linked to one of the faces of this texture cube. Yeah. Okay. So, and obviously we didn't have that technology before. So we got to go into depth stencil, and we see that we have added another constructor here that takes a com pointer to texture 2D and also takes in the face index here. So that is a constructor. This is a base constructor for depth stencil. And then the output only depth stencil has the same interface, and it will just pass that on to here. So if we look at this one, if we look at depth stencil.cpp, output only depth stencil passes on to the base depth stencil constructor. And in the base depth stencil constructor, here's where the interesting stuff happens. We are going to get a view, depth stencil view, on that sub resource in the texture cube, in the 2D texture array. So how does that work? Well, D32 float, that's the type. Nothing strange there. So for the view dimension, we got to tell it, okay, we want you to have dimension texture 2D array. MIP is 0. There's no MIPs with our depth. That doesn't matter. Array size 1. So this is very important because you might want to put a 6 in there because a texture cube is it's got 6 textures in an array. But no, this view only is a view on a single texture. So we say, okay, we're viewing a single texture. And then the first array slice, the start, is going to be the index that we were passed in. So we're viewing a single texture starting at this index here. And then we create the depth stencil view, and there we go. We've got a bindable depth stencil that is, the view is looking into the texture from this depth cube texture bindable. There you go. Let me tell you, it might seem pretty straightforward just when you have it explained out to you like that, but when you're just starting off, you don't know how to create this depth stencil view into a texture cube, it could be pretty tricky. So yeah, take heed. This is the standard way to do this, and it works quite well. Save you some time. Your chili's saving you some time. All right, so now we got these shiny new bindable components. Let's put them to use. So in this commit here, what I've done is I've implemented the omni-directional point light shadowing effect, all the machinery that goes along with that. So I mean, most of the heavy lifting of this is going to be happening in the shadow mapping pass. So what are we doing here? Well, we're going to replace some stuff. Now, instead of having a shader input depth stencil, we are going to be, we got a P depth cube. Where's that? It's got to be something in here, right? Yeah. So we got a shared pointer to our depth cube. We're going to store that as a member. The vertex shader for this pass is going to be Shadow VS, which is a new vertex shader that we've created for this, cube map, shadow map thing. There's too many maps, man. Too many maps. Anyways, null pixel shader as usual. Yeah, stencil, blender, sure. We have to adjust our viewport now because we're rendering to a cube map. All the faces obviously are not going to have the same dimensions, the same viewport dimensions as our standard rendering screen. So we need a viewport. It's going to be square, width and height, and all that good stuff. It's going to match the dimensions of our shadow map. So we've got to create this. There's a bug in here. It'll be fixed later. Don't worry about it. So we register the depth cube texture as a source because that is going to be consumed by our standard Lambertian pass. It's going to use it as the shadow map texture. So it's got to be available in the render graph. So we do that. Now we've got a lot of things that we're setting up here that are going to be used for generating the shadow map cube texture. So the projection matrix is going to be the same. We have to render the scene 6 times, one for every face of the cube. So we're going to have to, change the orientation of the camera for every direction that we render in. But they're all going to have the same projection, and it should be a square projection. Should have a field of view of pi over 2 or 90 degrees for you plebeians out there. And the reason for that is, it's because it's a cube, right? The edges of a cube, they're 90 degrees. You know what I'm saying, right? You know what I'm saying. This, by the way, is not correct. There's a problem in here. See if you can spot it. It'll be fixed later on in this video. But yeah, so projection matrix is the same for every face of the cube, but every face of the cube is going to have a different direction in which to render, and there are going to be some of them are going to have different camera up vectors, right? Because we're going to be using the function matrix look at left hand, and that requires a camera position, it requires a position to look at, and it requires a vector direction to control the up of the camera. So normally, if we're looking north, south, east, west, which in our case would be, in the X directions or in the Z directions, the camera up would just be positive Y. And you see here, we got positive Y here, positive Y here, positive Y here, positive Y here. These are the Z, these are the X. But when the camera is pointing in the Y directions, up and down, the up of the camera cannot also be up or down. That's no good. So you've got to put it in different places, and I put it in these places. They were wrong. We'll fix that later on. I basically just guessed because I knew I could fix it up later on anyways. But yeah, we've got these vectors here. And now basically for executing the pass where we actually capture the depth into our shadow map, we're doing a bunch of manual stuff here because it doesn't quite fit into our render queue stuff. So cleanly, we have to select every face of the cube, and we have to set up our view transforms. So what we're going to do is first we're going to set the projection that we stored in the constructor here. We're going to set that on the graphics. We're also going to ahead of time load the position out of the camera. Then we're going to loop through all the faces of the cube. For every face, we're going to get out a shared pointer to that bindable, that shadow, whatever, depth stencil bindable. We're going to clear it. we're going to set it as the depth buffer for this pass. And all that is going to do is it just calls this function here, which sets depth stencil to here. It does a little bit of stuff with const cast because, you know, this is const. You're not supposed to change member variables, but this one's kind of special. So we're going to let them change it, right? Doesn't matter. So we set the depth buffer. That's when we're going to be used when we're rendering. Then our look at position is the position of the camera plus the viewing direction, which is just a vector that's pointing, you know, 1 unit in the direction that we want to look. And so then we have our look position. We're getting some crazy thunder outside. I don't know if you're picking that up in the microphone, but anyways. Then we do our look at. We set our camera matrix as this vector here. Starting camera is at position. It is looking at the look at point, and the camera up is loaded from our generated array of camera up vectors. And then we execute the render pass, which is going to, you know, draw all the drawables. I'm going to render them. I'm going to build up that depth buffer. And that's basically it. Viewport.h is a new bindable, setting the viewport. This is wrong. This is kind of an artifact from a previous attempt that I made, but it'll be fixed in a future commit, so don't worry about it right now. We have the viewport. Cube texture, just a small adjustment to make it return a shared pointer instead of a reference. Blur outline render graph. We just comment out the code here for dumping a shadow map because that function does not exist on our current shadow mapping pass. Binding pass, when I was doing some debugging, I noticed that something that was no except should not be no except. It was, you know, stifling my exceptions, so I fixed that. But that's it, basically. Nothing major there. The only major changes are in shadow mapping pass and in our shaders. So we got a new shader, shadow vertex shader. This is the vertex shader that we use when we are capturing the shadow map. Now this one requires a little bit of explanation, a little bit of diagrams, I guess. So imagine you got this set up here like we had before. We got a light here. We're capturing a shadow map like this in a single direction, and then we're going to render the scene. This is the actual camera from this point of view. So when we capture the shadow map, what we're doing is we're capturing depth this direction here, right? So capturing depth in the Z direction from the point of view of the shadow mapping camera. Then when we render this, what we're going to do is we're going to map this point again into the space of the shadow mapping camera here, and we're going to measure this distance here, and we're going to compare it to the distance that is in the depth texture, whatever you want to call it. Right? Here's the thing. Imagine now your shadow map is a cube. So here's a point that's going to be rendered. Here is our camera. So what we're going to do when we capture this depth, well, if we capture the depth as we've been doing before, what we would do is we would render this for this face of the cube. Depth would be the Z, right? Just normal rendering with depth as Z. That will be recorded at this point here in the depth map, shadow map. Yeah. And then here's the problem. When we render this from the point of view of the camera to do our Lambertian rendering, to sample from the cube map, what we're going to do is we're going to basically get a vector from the light source to the point of interest, and we're going to use that vector to sample into the cube texture. Now here's the thing. From this, how do we figure out what depth value we need to compare with the depth value in this texture? You might say, okay, well, chili, that's easy. It's just this length here. But here's the thing. When we're sampling into this cube, we don't actually know ahead of time which face it's going to hit. If the point were here, then maybe it would hit this face. If it would hit this face, we would have to measure this distance. But if it hits this face, we have to measure this distance. They aren't going to generally be the same. So whenever we sample from the cube, we'd first have to figure out which face this vector is going through. I don't have to do a bunch of math in my pixel shader when I sample from my cube texture to figure out first which face the sampling vector is passing through, and then from that figure out which orientation I need to use to calculate my depth to compare with the depth in the texture. I don't want to do that. I just want to have a vector, sample this, compare with some simply calculated value, and be done with it. So what we're going to do is, instead of storing in here this straight line, quote unquote Z depth, we're actually going to store the linear distance, the Cartesian distance between the light and the point of interest. So if we store that distance, then when we render from the point of view of the camera, we can just calculate this distance again and compare with what's in the texture. We don't need to worry about which face it's going to be sampling into on the cube. Doesn't matter, because no matter which face it samples into, the distance between these 2 points is the same. And that is what we're doing here. So we're actually going to take the length of the view position, which is the position of the vertex relative to the camera. And to take that length, that's the distance to the point of interest. Now here's the thing. If I store this in Z, what's going to happen is it's going to be perspective divided by W. So what I'm going to do here is I'm going to pre-multiply by W in order to counteract that effect. The other thing is that if we just put the length in there directly, lengths greater than 1 would be clipped away. We'd have a very, very close clipping plane effectively. So we're going to divide by 100, and that will put the far clipping plane for our depth values that we're recording. They'll put that far clipping plane at 100. Now that actually has an interesting effect because we're not measuring depth just in the Z direction, but actually taking, the 3-component, the Pythagorean distance or whatever. That means that instead of depth, the far plane being a plane, the far quote-unquote plane will actually be a kind of paraboloid like this, or an arc, I guess you would say. So our far plane now should look something like this, interestingly enough. At least for the purposes of shadow rendering. It won't change anything for our actual Lambertian shader rendering. But yeah, so there's the most complicated part of this out of the way. So for the VShadow shader, what does this one do? This one converts shadow to homogeneous space. This is for the Lambertian shading side. Now, because we're not converting to homogeneous space, we're just converting to camera space, basically. We just need a vector in camera space to sample into that cube map. So we're not going to be doing, any of this hanky-panky. All we're going to do is do our model transform, bringing points from model space into world space. And then we're going to translate those points so that they're relative to the camera. I call it shadow position for whatever reason, doesn't matter. It's the position of the light, basically. So we're going to make these ones relative to the position of the light. And then in the code here, for the pixel shader side of things, we're not going to be doing, I've basically removed a lot of stuff from here. We'll be adding some of it back. But basically all this stuff is just going to turn into a single call into sample compare level 0. We're going to be sampling using the sample comparison state, same as before. The texture shadow map is going to be now a texture cube. We're going to use the XYZ of the positioning. We're going to use the length of that vector divided by 100 as the comparison value. And that's to compare, that will compare, or it should compare well with this value here after it's been, divided by W. Now, judging from the name of the commit, you can probably guess that we've got problems. And I mean, if we look at this light here, yeah, these shadows, I mean, it's casting shadows. They don't seem to be corresponding to the geometry in the scene. So we've got some issues. Basically, it's time to get debugging. Now, my first step try to do was I figured, okay, well, I want to dump all the faces of my texture cube so that I can see what I'm working with to begin with. So I reinstated the ability to dump texture cube. Basically what I did was I re-implemented dump shadow map so that it loops through all of the faces of the cube, gets every individual buffer, calls toSurface, calls save, and Bob's your uncle. When I did that, what I found was that every single image was identical. So it was just saving the same member of the texture array. It was saving the same 2D texture 6 times. So that made me realize, that led me down a little bit of a rabbit hole into figuring out how to actually map into the individual parts of the texture array so that I can, convert each one individually to surfaces. So we go into depth stencil, to surface, and what I'm going to do is I'm going to get the descriptor for the depth stencil view. This stuff is the same, I'm just getting the descriptor for the 2D texture associated with that view. But the thing is, if I get the descriptor for that texture, it's going to give me the descriptor for the entire cube map, not just the sub part of it that I want. So what I have to do is, okay, I get that descriptor, I overwrite some of the things here, like the flags, because I'm going to be using this temporary texture descriptor. So what I do is, okay, yeah, so I get this source descriptor, I copy it into a temporary texture descriptor, and I overwrite the standard things, the CPU access, the staging, bind flags. I also overwrite the miscellaneous flags, because remember, the miscellaneous flag could be a cube, and I don't want to create a temporary cube, I just want to create a single 2D texture. And I overwrite the array size to be 1, because if this input, if it's a cube, then this is going to be 6, and this is going to have the cube flag. So my temporary should just be a simple 2D texture. I create my temporary. Now here's where things get interesting. What I'm going to do is I'm going to check that view descriptor that I got up here. I'm going to check it to see if it is a 2D texture array. If so, that tells me, okay, I'm dealing with a cube. So what I should do is I should actually copy SubResource region. So don't copy the whole thing, just copy a part of it. So we're going to copy into the temporary texture. We're going to copy from the source, and the index is going to be the first array slice member of that descriptor that we got. So this is going to tell us which member of that array we're going to be copying from the source into the destination. These values here, they're just for more finely controlling sub-resources, for controlling, like if you just wanted to copy a sub-rectangle of one resource into another or whatever, that's what you would use these values for. But we don't want to do that. We just want to copy one member of the array from the cube array into the single temporary texture. And of course, if our view dimension is not texture 2D array, then we're just going to do our standard copy resource, copy the whole dang thing. This is just some renaming that I did, nothing big. But yeah, so I did that. That enabled me to actually output my my stuff, my good stuffs. And what did I do? I created a window that allows me to click a button. And when I click that button, it's going to dump the shadow map. Put it in a folder called dumps, like that. And what does it look like? Well, here's what it looks like. So what I did, I should mention this actually, because it's important, but to simplify my debugging, what I had done in the shadow mapping pass was here, I make it so that it clears all the depth buffers, but it only renders to the first one. So I just wanted to start off dealing in one direction. Once I got one direction working, then we can start on in sync. Ba-dum-tis. Anyways, so what did we get when we captured? Well, obviously these ones are all empty because I'm not rendering to them. This one, yeah, okay. There's like a huge part that it's not rendering to. And that led me to look at my viewport. And when I looked at my viewport, what I noticed was it's dumb because it's not taking in the proper width and height. The whole point of having a viewport bindable is that so I could set different widths and heights for, specifically for when I'm doing my shadow rendering. So we make the viewport take in width and height and use that. In the shadow mapping pass, we use the size of the shadow map as the width and height of the viewport. And now when I render my boy, he's using up the whole portion of the square texture here, instead of having this dumb white stuff on the bottom. So that's one part of our problem fixed. Now, here's the thing. With spoilers, I'm not even going to show it to you, but it's still not working. The shadows are still all messed up. They're not even close. So there's another problem. To fix this problem, I ran the graphics debugger. I stepped through the shader. I looked at my values, and specifically, I looked at the values coming out of my Vertex shader for my shadow rendering, and they were bad. So I looked at the operations on them, and the matrix, the transformation matrix for transforming my vertices into the space needed for shadow mapping were messed up. So I looked at what was binding those matrices to the pipeline, and it was this bad boy here, shadow camera cbuff. And lo and behold, it's getting the entire transformation matrix from the camera plus the projection from the camera. We don't want that. Our projection is to be set by the shadow mapping pass itself is setting that projection. Step 1. Step 2, the matrix. We don't want all the camera matrix stuff, the rotation of the camera that's affixed to the point light. All we want is the position. That's all that's important. To simplify things as much as possible for rendering our cube map, our depth cube map, our camera points in the positive X, the negative X, the positive Y, the negative Y, the positive Z, the negative Z. So we don't need the rotation of the camera. The orientation is always the same for the 6 faces. The only thing that changes is the position of the camera that is at the light source. So we encode that as a translation opposite of the actual position of the camera in the world. That translates everything in the opposite direction relative to the camera. So it brings everything into the camera's space in terms of translation. And we weren't doing that, so obviously we were getting messed up results. So we do this, and now you see, again, we're still only rendering the positive X direction. But you can see, okay, we're starting to get somewhere. Let's turn up the shadows here. Let's turn up the lights so that the shadows are actually more, visible, I guess. I don't know. We can see, okay, so it's kind of close. It's not quite there yet, obviously. I mean, yeah, we're not quite there yet, but we're close. Things are starting to make sense. So what is the missing piece of the puzzle? And I'm just going to tell you, there was no standard procedure or like stages of deductive reasoning that led me from looking at that image directly and inexorably towards the answer. I just kind of looked at it for a while, and then I started thinking to myself, getting kind of pissed off because, I'd fixed a bunch of bugs and there's still little bugs. And then it just kind of dawned on me, just out of the blue, my projection was wrong. I was looking at a bunch of different things, thinking a bunch of different things, and it came to me, yeah, this is wrong, right? So matrix perspective LH, width and height of 1, that's okay. You want it square. But the near Z of 1 is no good. Why? How sway? Well, think about it. We got a cube. We want to render so that all the faces are going to have the same size. It's a cube, right? They're all going to have the same dimensions. That means this angle, all these angles here have to be 90 degrees. Which if you're a baller, you say that's pi over 2, but whatever. And 90 degrees. What does that mean? Well, that means that this distance has to be the same as this distance. Well, if this is 1, then this is 0.5. So this should have been 0.5, but I made it 1. Making it 1 would, if this were 1 and this were the same width, then your field of view would be wrong, and your projection would be wrong, and your shadows would be off. They'd be close-ish, but they'd be off. And that's what we're seeing. So, to make a long story short, you make that 0.5, and Bob's your uncle. And reinstating for all directions, yeah. So down here, we remove this thing here, so now we're going to loop through all of the faces of the cube. I'm going to clear them all. I'm going to render them all. Then we're going to have an entire cube. We can use the whole cube to map shadows for the whole scene. And so here's where we're at right now with that scene. Okay, so let's turn up the contrast. Give ourselves a little bit more dramatic shadows here. And this looks good. Let's look behind the curtains. Yeah, this is looking real good. This scene is looking properly lit. Like, this is lit fam and also shadowed, which is like two sides of the same coin, if you know what I mean. It's beautiful, except, well, I mean, there's some weird stuff here, right? This is weird. That shadow up there is weird. What is all this stuff? Well, let's see here. Do a little experiment. I'm gonna move the light up a bit. Okay, that's weird. And then what we're gonna do is let's move this around. Which one is that one? I think it's cube 1. So, this is weird for obvious reasons. That's very strange, right? There's something wrong with the orientation of the shadow map for Y down and probably for Y up. And this basically goes back to what I talked about a little earlier. And that is when you're Y up and you're Y down, your camera up vector can't be Y up or Y down. It's got to be something else. And I didn't really think it through. I just kind of did whatever. So I looked at this and I fixed it. Did a couple other changes too. I turned off those camera indicators by default here because we weren't really using them. They're just kind of annoying. I changed the function used to generate the perspective from this one to a field of view. So I'm explicitly now saying that I want a field of view of, pi over 2, 90 degrees. And that's a little better. It's the same thing, just a little better way of writing it in my opinion. And here I fix those pesky up vectors. So what were they before? So I was using positive X as the up vector and decided to use negative Z, and here positive Z. And here we have the current state of the shader. So shadows are working real nice here. Beautiful. That's beautiful. That's beautiful. Take a look at the view here from the second floor. Yeah, it's looking real nice. Shadows going in all directions. It's looking properly lit now, but from before we're getting light in places where it couldn't possibly have been reaching. But now that we've got all that occlusion in all 6 directions of our cube map, it's working fine. And yeah, if I move cube 1 around a little bit here, let's move it underneath our light source, we see that it is actually casting a proper shadow. So all the maps are correct. Now there are some problems here, and it's still in the work. What is this? I don't know what this is. I'm still working on it, to be honest. But there are artifacts in rendering the shadows here, especially when they get close to a surface. They seem to be casting artifacts on them. Yeah, like look at that. I don't know what that is or where it's from. I'm gonna have to do a little bit more debugging to get down to the bottom of things. So it's almost working 100%. Bug to fix, and also we turned off our PCF, so this ain't looking too great. We want to re-enable our PCF, take multiple samples, but it's not as easy as you might think to take multiple samples of a cube map texture. It's a little more complicated. So I think that's what we're going to look at in the next video. We're going to look at PCF sampling of our cube map texture, and we are going to get to the bottom of this, because I still don't know what this is. But if you're interested, you can try to figure it out for yourself. And if you figure it out, you could even let me know, because I mean, that would save me some time. I've been pretty super busy these last few days. So if you're watching these videos as they come out, you'll notice that this one, quite a few weeks between the last Hardware 3D video and this one. So yeah, it's a combination of just, having less time to work on it, and, running into progress blocking bugs. So yeah, I issue an open challenge to anyone who wants to try to debug this. If you want to, by all means, have at it and let me know if you figure out But at any rate, I'll be taking a look at it myself, and that's what we're gonna be talking about in the next video: debug and a PCF. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you with some hardware 3D.